Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. I have Rahul Panat. He's an associate professor of mechanical engineering at Carnegie Mellon University. We're going to be talking about his work: microscale additive manufacturing, flexible and printed microelectronics, and advanced energy materials. So, Rahul, thanks for coming. How are you doing?
Yeah, thank you. Thanks, Richard, for having me on the show.
Yeah, tell me a bit about your research. What kind of materials, what kind of uses are you looking into?
So, I work on micro and nanoscale 3D printing using nanoparticles to fabricate devices with newer functionalities and features. That's kind of the overarching theme of my research. In particular, the focus is on using this technology of micro and nanoscale 3D printing to create new types of biomedical devices, or giving additional functionalities to biomedical devices, getting high-capacity lithium-ion batteries, and creating more sensitive sensors for various applications. So essentially, I'm applying the advances in micro and nanoelectronics manufacturing, advances that are happening independent of the application space, right, to these specific application areas.
So what kind of additional functionality are you looking to create, or you have been able to create? What are some of the big important things that industry wants?
Right. So I'm going to give you an example of what we are doing. So my group is working on using a droplet-based additive manufacturing method to create three-dimensional structures. And it turns out that these three-dimensional structures can build microscale needles that are used as brain-computer interfaces. And my group was working independently of creating these three-dimensional structures without really focusing on applications, because that itself involves a lot of droplet dynamics and also sintering dynamics. But once we were able to create such needles, it turned out that we were able to create brain-computer interfaces with highest density of electrodes that people have yet been able to create. In other words, lithography, which is a traditional method of making microelectronic devices, was able to create some brain-computer interfaces with electrode densities of 100 to 500 per centimeter square. And by printing in 3 dimensions at microscales, we were able to increase that density to close to 6,400 electrodes per centimeter square, and also create customizable brain-computer interfaces that would be used in applications such as neuroprosthetics, stimulating neurons, and so on and so forth. Yeah.
Well, tell me a little bit about the needles themselves. How long, how wide, or circumference? How big are they?
So these needles have a diameter ranging from 20 microns at the base to the tips are about 10 microns in diameter. There could be larger needles as well, with about 40 to 50 microns diameter. And the typical length we have is several millimeters. So we are talking about length between 2 to 3 millimeters, and then these would be recording signals from a brain. At this point, we are looking at mouse brain. But this shows that these newer microelectronics manufacturing techniques that we are working on, when they are applied to these newer fields, it can create really amazing device applications.
So I would guess there's a trade-off. If the needles get too thin or too long, if the ratio is off, that they'll bend under pressure of insertion. So how do you accomplish that where they have strong enough tensile strength or whatever, non-bending strength that they can go into a substance?
Yeah, so we just recently published a paper exactly on that area. So these needles or micro pillars, as we call them, you can tune their properties by different thermal treatment or sintering conditions. In other words, our microscale 3D printing technique, by the way, it is called aerosol jet 3D printing. We we assemble nanoparticles in three-dimensional space in the form of a needle. But these are nanoparticles that are separate from each other. These are metallic nanoparticles. When we sinter this structure, the nanoparticles fuse together and start to grow. And between 200 to 300 degrees Celsius of temperature, there is grain growth dynamics that allows us to create stronger needles that do not break even when they are bent to very small radii. So small radius means there is a large amount of strain in the system under bending. So basically, this microscale structures with nanomaterials, we have pretty good handle of input conditions or control parameters by which we can tune the properties for a specific application. In this case, it's insertion into brain tissue. And by the way, brain probes is not, or the brain-computer interfaces is not the only application we have applied this technique for. We also have high-capacity lithium-ion batteries and more sensitive sensors that we fabricate using this method.
So besides being strong enough to be inserted into a substance, what other properties do you want to tune with these needles? Is the taper important? Is the certain long lengths needed for certain applications?
Absolutely.
What else?
Absolutely. That is the beauty of 3D printing, is that we can actually create a computer program, feed it to the machine, and at a click of a button, you can create three-dimensional structures without any support materials in our case that can give rise to different shapes. In this case, for example, sharper tips can give rise to easier insertion into the brain tissue. Or we can also create, for example, complex three-dimensional structures with extremely high surface area for the structure, which can have higher sensitivity, for example, in detecting some biomarkers or some kind of physical or chemical signals. So, yeah, does that answer your question?
Yeah, I just wanted to know some of the tunable parameters. Okay, that makes sense. So, in addition to the needles, what other types of nanomaterials are you working with, and what would be their functionalities?
Right, I'm working with printing of some gold, and as well as my group is planning on using platinum. For example, platinum is highly biocompatible, so that's a material that we would want to have. My group is working on printing of 2D materials, which have certain advantages in terms of certain properties. My group is working on printing of several types of polymers so that you can create multi-layered PCB boards, fully printed multi-layer PCB boards that can accompany the devices that we are also printing. So, these are the kinds of materials we are currently working with. So in polymers, we print polyimide, we print SU8 polymers. We also print acrylated urethane. Some of these can be cured by UV light. What that does is we are able to create different three-dimensional structures, such as optical waveguides, that would be very difficult to do by any other method. And then droplet by droplet, we would create a three-dimensional structure of polymer, for example, in this case. Yeah. So our focus at this point is on printing of metallic materials, polymers, and we are moving towards 2D materials. We haven't printed ceramics yet.
So a waveguide, what for people that don't know, what what would be the usefulness of a waveguide? And it sounds like you're able to do it in a 3-dimensional way instead of 2-dimensional, or a
That's
more
correct.
sophisticated way. Like,
So,
what would be the benefit?
yes, yes. So typically, waveguides are narrow tubes of material that can carry light through total internal reflection. And if we are able to steer light in any way in 3 dimensions, then there are certain advantages. For example, right, the brain probes, the metallic brain probes I told you that can capture electrical signals or that can stimulate the neurons, we can also integrate the polymer probes along with them. And in certain types of mice, certain types of genetically modified mice, we can actually stimulate neuronal activity by exciting certain portions of the brain by using these optical waveguides. And this is basically, as you know, right? Everything that we do and work is controlled by neuronal firing or activity inside our brain. But what triggers that activity is not a very well-known thing. So in certain types of genetically modified mice, there is an entire area called optogenetics, where we can actually induce neuronal firing patterns by just shining light in those regions. So the optical waveguides can be printed, and those can be then inserted into the brain, a mouse brain, for example, to see what happens when neuronal activity in certain area is triggered. So I work from the device side for this problem, and I collaborate with a neuroscientist to study what the effects of all these devices would be.
Yeah, you also talked briefly about creating, I think it was 3D polymer structures.
Yes.
So what would those be used for? What kind of applications? And I'm sure some of them are just naturally 3D because of the bond angles. But what do you envision, and what would you be able to do that's more sophisticated?
So for 3D polymeric, polymeric structures with, let's say, a pillar of polymer which is 100 microns in diameter or 50 microns in diameter and 1 millimeter or 2 millimeters in length can be used as an optogenetic stimulation device, as I mentioned before, right? There could be other applications where we mix certain functional particles into the polymers and create 3-dimensional structures. For example, I can mix polymer particles into, magnetic particles into a polymer and print it in as a 3-dimensional structure, and that can be used as a microactuator, for example. There could be other applications such as mixing nanoparticles, some kind of functional particles, again, into the polymer and printing it on a robotic arm, for example, where it acts as a tactile sensor, for example. Yeah.
So what are some of the challenges in working with the size regime of the particles you work with? I've heard that forces on a macro scale are very different from a nanoscale. So, what's unique to the size range of the things you work with?
Right. So, every size range has its disadvantages, right? Nano and micro scales are very difficult to handle. But at the same time, micro and nano scales can give you huge advantages that you would never see in macro scale particles. For example, the 3D printing method that my group has developed, where we can create 3-dimensional metallic structures without any support material, they work on the principle of droplets getting extremely sticky when they have a very small diameter. And I'll give you an example of an example that we observe in nature. In nature, right, in Namibian desert, there are droplets that contain sulfur, okay? And these get driven by a wind into deserty area, right? And as the heat goes up, these droplets kind of the water or the solvent portion is evaporated, and the sulfur falls on the sand. If there is no seed there, then this would just not result in anything significant. But if there is a seed that forms over millions of years, this gives rise to very beautiful three-dimensional structures called desert roses. Essentially, this whole thing happens because these droplets are in micrometer length scale, where their stickiness or surface forces are much larger than their weight, which is the inertia forces, okay? So we use exactly the same principle. We have these droplets of solvent that contain these nanoparticles. They are driven by a gas in this aerosol jet microscale 3D printing machine. And when they drop on a platen, for example, or a substrate on which we are building the device, instead of falling down and creating a planar structure, if there is a seed, we can build three-dimensional structures where the droplets don't just fall down, but stick to one another and form a beautiful, very complex structure. So at these length scales, there are challenges, of course. For example, control in dimensions, control in overspray, and all these challenges. But this length scale also provides advantages that we use in order to create these device classes.
Well, I mean, making a beautiful structure is one thing, I guess, in photographing it. But what would be the use of these solvent microstructures that you're making? What's the use case?
One of the uses is obviously the brain-computer interface, right? I can create three-dimensional needles by using this technology where the needle density is more than 10 times anything that lithography can make. The second huge advantage is I can create a very complex microlattice structure, which would be very difficult to do by any or fabricate by any other method, and use it for lithium-ion batteries where I have extremely high surface area and my electrolyte can penetrate through the volume of my electrode. That will reduce the stresses, that will provide nearly 100% electrode utilization, and that can provide higher power or areal densities. I can use this very phenomena to create high surface to volume ratio materials for improved sensing purposes. And in fact, we demonstrated a battery where we showed 100% increase in areal density when we use microlattice structures versus just planar block structures that conventionally are being used.
Yeah, that's what I was going to ask you, is how much more dense, how much stronger, for instance, can you make certain materials? Like, if you can put orders of magnitude on it or numbers generically, how much improved are the materials you're making?
So, for example, I would measure the improvement in terms of the functionality that these materials provide, right? So in brain-computer interfaces, we have customization, and as well as we have more than one order of magnitude increase in the electrode densities that we can interface with the brain. In case of lithium-ion batteries, we believe that about 50% increase in the capacity is we will get by using this microlattice 3D or 3D printed microlattice batteries, which also translates into reduction in weight for a given capacity, right? And in case of, let's say, strain sensors, for example, we demonstrated that 3D printed porous films have a 57%, about 60% improvement in the gauge factor, which is sensitivity of the sensor. So these are some of the numbers that roughly represent what the types of devices we can make by using this droplet-based microscale 3D printing approach.
Yeah, and I guess in the example of a battery, I'm sure it's obvious to you, it's not just two-dimensional higher density, but it could be three-dimensional. Perhaps you can make very dense three-dimensional structures that would work in the battery instead of relying on just, again, two-dimensional increase in density.
Absolutely. And this technology absolutely allows us to do that. And by the way, these microscale 3D printing method, we can pretty much print any material that can be crushed into nanoparticle format. nanoparticle form. So so this is a improvement in battery capacity purely by change in geometry. There is no change in chemistry of the electrolytes or transport properties of ions in the batteries. If you know that that's something kind of sounds important because it is important to create manufacturing methods that are independent of the materials that are being used, rather than dependent on certain types of materials or chemical compatibilities.
So how do you get the nanoparticles all of a similar size, and how do you get them where you want them to go and keep them in a certain area? Do they tend to run away on you or, have other issues?
So nanoparticles can never be made with the same size. Anybody who claims that is perhaps not telling the truth. So nanoparticles always have a large size range. So when we purchase, these are commercially available nanoparticle solutions. So these are dispersions. Every nanoparticle is decorated with a chemical that separates them from agglomerating. And we have certain methods here, such as tube rollers, on which we put these solutions so that the mixing kind of continuously happens before we load them into the machine. But these are commercially available nanoparticle solutions, and we have been purchasing these and using certain types of solvents to print them.
What is the typical size distribution? Oh, sure. Yeah. No problem.
Yeah. So maybe Rickard, I wanted to also mention about my background, how I came from industry, by the way. So
yeah, let's do that. We'll insert that in the beginning. Tell me a little bit about your background.
Yes. So I currently I'm an associate professor of mechanical engineering at Carnegie Mellon. But prior to becoming a faculty member, after my PhD, I directly went to industry. And for 10 years, I was working on microprocessor and IC fabrication technologies at Intel in Chandler, Arizona. So at Intel, it was kind of a heaven for micro and nano manufacturing because you had to make these computer chips, package them in certain form. You had to connect them to external world, look at the reliability problems, and so on and so forth. And what I learned, the key thing I learned at Intel is that there are several micro and nano fabrication techniques or manufacturing methods, and there are many new ones that are coming up on the horizon. And I wanted to explore some of these new methods myself. And one of these methods was micro and nanoscale 3D printing, where the speed is slow, but at the same time we can create different device geometries. We can combine different materials that it would be impossible to do using conventional lithography. And we can create microstructures that would be very difficult to control by conventional lithography. And that is the desire from my side, as well as my desire to interact with students and kind of develop, mentor students essentially and teach, is what drove me to come to academics. And that is how I chose this area of micro and nanoscale 3D printing.
Okay. Yeah, what excites you most about the possibilities of what you're doing? Is it the stuff you've already talked about, or is there something else that maybe is out of reach right now that you're so thrilled if you can do it?
Sure. I'll give you an example of what I'm working on. One of the examples is I'm creating these electronic decals, which are extremely miniaturized devices that can be put on skin and that can capture vital biomedical vital biomarkers. Now, what excites me about doing all these things is what types of changes this is going to bring to people, right? So one of the things is these decals will allow people or older patients or older people with certain chronic conditions to be in home care versus being in hospital care. So that kind of impacts people's lives, right? I'm also working with some doctors to look at deep brain stimulation probes for patients who undergo periodic seizures in epilepsy. And again, these are all 3D printed devices where we are looking at being able to cure or ablate the part of the brain that is showing abnormal activity by minimal surgery versus today what happens is a large surgery where part of the skull is removed and part of the brain needs to be removed in several severe cases. People will be able to do that with a smaller surgery, for example. In brain-computer interfaces, the kind of functionality it will bring to people with neuroprosthetic devices. These are all the things that really, really excite me because ultimately we are people, right? And bettering people's lives is what is really the ultimate goal that my group is working towards, and it's an immense satisfaction, to say the least.
Yeah, no, that's great. But what do you think will be possible for your lab and your research in the next few years? And then maybe one more counterexample of what do you think is still pretty far in the future, but would be great to do.
Yeah. So one of the key things my lab strives to do at this point is I came from industry. I came with the latest and greatest knowledge in microelectronics manufacturing. And when I look at all these biomedical devices, I visit hospitals around CMU in Pittsburgh area. By the way, Pittsburgh is a huge hub of medical research, hub for medical research. I see that the devices people are using have really, really primitive electronics in them. And part of the reason is the long FDA process of approval, and part of the reason is that not many engineers have seen these devices and have seen where they are used and what kinds of effects they can have on people's lives. So my group's overarching kind of aim is to bring newer electronics manufacturing technologies into the biomedical device fields to better people's lives, as I mentioned before. And what is not possible is, I would say that perhaps what is not possible is coming to a full conclusion. In other words, right, all different types of diseases, different types of conditions keep on popping up all the time, right? We are seeing that with the coronavirus outbreak. So medical device field will always need to catch up with the diseases and ailments that come up, right? And we as engineers who have knowledge in microelectronics and nanoelectronics manufacturing will have to catch up with these devices or the requirements of these devices. So it's a continuous process, I feel.
Yeah, as you were talking, I imagined, the pore size of various parts of our body. I wonder if you can make objects that would be small enough to just enter through our pores, through our skin pretty easily, and then maybe they're guided externally by magnets or, electric field or something to migrate to a part in the body and accomplish some task. Or maybe once they're in the body, they, the particles open up or degrade and release kind of a drug. I mean, I guess there's a lot of things that can go on.
Yes. I think, this is a very a broader outcome, and that is definitely possible. And what my group is working, so my group is not working on anything specific that would do what you just mentioned, but my group is working on miniaturizing device technologies, right, or device form factors that would be a vehicle to achieve some of the things that you mentioned. So, for example, the brain-computer interfaces are invasive today, right? Or even the DBS probes that we are using for working towards for seizures still require a level of surgery that is much less severe than removing part of the skull. But going everything towards kind of an inserted device that monitors the vital signals in specific parts of the body is very much possible. And the technologies created by my group will form kind of a platform for doing exactly the same thing.
Well, very good. Well, Rahul, what's the best way for people to see or experience your research? Do you have a website URL, or where could they go?
Yes. So on my CMU website, there is a video about my research. There is also a video about my teaching where I force students to, in my courses, I ask students to do the engineering research, or rather engineering analysis, but ultimately they have to get to a product that they can sell. So there is a video about my teaching as well on my website, and my group's website is advancedmanufacturing.us, and that website lists all the research areas that I have been working on. Yes.
That's great.
Yeah, my research has been funded by National Institutes of Health, National Science Foundation, and the U.S. Department of Energy. And also hospital chain Highmark is funding some of my research, as well as some other agencies as well. So I really want to thank them for having faith in people who are working on new technologies, because it's not always easy to invest in what is going to come up in future, right?
Well, very good. Well, Rahul, thank you for coming on the call. I appreciate it.
Yeah, thanks a lot, Richard. I really appreciate this podcast. Yeah.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.